So yeah, I wanted to say a couple of words in German today, but I asked a local friend and I don't think I'm able to, so sorry in advance. But yeah, instead, let's talk about how to master CustomPainter without it mastering us, right? With a special focus on the draw path method. But first, let me introduce myself. So my name is Sofia Rey. I come from Uruguay, South America. I'm a mobile engineer at Very Good Ventures. I've been working with Flutter for more than 3 years now. And as a curious fact, I'm also, as a hobby, I study multimedia design, which is also why I find paths pretty interesting, as I believe they live like in a sweet spot between design and programming, right? But let's get into the topic. But first, why should we use CustomPainter? So let's imagine our designer sends this UI. So it looks pretty doable with Flutter, with just simple widgets. But what happens if then he asks for something like this? Or if Sean's picture is a bit more organic? We also have other use cases, for example, charts, speedometer, custom controls, or, which was my case, and a little sneak peek into today's demo, a track map for car races in which the cars has to follow a specific path, right? So this is what we are gonna be working on today. But first I'll go through, spoilers, sorry, through all the tools we have available with CustomPainter. So when the designer asks for something like this, we really have two options. The first one is just to say, nope, we don't have the time. The second one would be to actually use CustomPainter. And if you chose this one, then this talk is for you. So let's get into it. But first, let's understand why CustomPainter is so powerful. And for that, I want to talk about the Flutter's rendering pipeline, right? Flutter works in trees. We have the widget tree, which is the one we as developers work with every day. So widgets are immutable classes, which means they can't change. So every time something changes in the UI, we have to create and rebuild each widget. But they are like Ghost performant, so it's fine. And then we have the elements tree. So we'll have an element per each widget we have. And elements are mutable classes. So they do update and they keep the reference of the widget. So they keep the widget's lifecycle. And this is what makes it performant, right? And finally, these elements will later transform into render objects. Not every element, because we have components elements that are just like contain other elements, but the render object element will transform into render objects. Render objects are also immutable classes, mutable classes, and they do the actual work of rendering, so they will do the sizing, layout, and painting in the screens. And how does CustomPainter fit into all this scheme? So, sorry, here's like a quick cheat sheet in case you want to go through it. I'll share the slides later with you. And this is, as I said, Flutter's secret formula for performance. So let's see the custom paint. If we want to use the custom paint, we will use the custom paint widget, which will create a widget in the widget tree, which will later transform into a render object element in the elements tree. And this render object element will create a specific type of render object that's called render custom paint. This render custom paint will go through the layout phase, but when it comes to the painting, there's gonna be like a small plot twist, and instead of doing it there, it will ask and delegate this task to the custom paint in the widget tree. So it's like Flutter gives us access to write painting logic almost like inside of the render objects tree. That's why CustomPainter is so powerful. So now that we get it, we can talk about it. What is it, right? So it's an abstract class that provides the extended class the access to the paint method. In the paint method, we are gonna have the whole custom logic for printing, right, for drawing. So this is how it looks in code. Here we have an example. I created a class called myPainter that extends the CustomPainter class. And we have to override some mandatory methods that we are going to discuss later. And to use it in our widget tree, we need to use the custom paint widget and provide the painter, in this case, myPainter, just the example, as the painter parameter there. And that's how we use CustomPainter. So what are the main methods we need to implement? The first one will be the paint method, which is where all the magic happens, basically, where we can write our custom drawings. And it will receive a canvas, which is the actual surface for the drawing, and will provide us with tools for that. And then the size, which is the available space for it. And then we have the should repaint method, which is very important for performance, as is the one that's gonna determine if we need to repaint our drawing or not. And the parameter for this one will be the custom painter, a custom painter that's the old delegate, so the previous frame. So we can use it to compare, like, did something change? Should we repaint it or not? And that's basically it. Then we also have some optional methods, like for the by default, the custom painter won't work with the usual interactivity user interactivity. Sorry, but if we override the hit test method, then we can know if a user tapped in a certain spot of our drawing. Then we have the getter semantic builder, which is mostly for accessibility. We can describe what we are drawing, and the screen readers can read it later. And we have the should rebuild semantics, which is the same as should rebuild method, but for the semantics builder getter. Now let's talk about the Canvas API. So what are the rules, and what tools do we have when drawing in Flutter? So let's imagine the canvas like as an actual painting or surface. We use a coordinate system in which the 0, 0 dot point is in the top left corner. And this can be a bit tricky to understand at first, but here's a quick example. If it says 15 on X, it will be like more to the right. And if it says 10 on Y, it will be more to the bottom, right? Then we have the drawing operations. As I mentioned at the beginning of the talk, I'd like to focus on the path part, but I'm going to do like a quick overview on all the tools we have available, just for you to know. So first, let's go through the basic shapes. So basic shapes all work the same. It's always draw something, and then we have a couple of parameters for position and sizing. And lastly, we have the paint object, which is gonna be give the style to this painting. So for example, we have draw rect, which will receive a rect object that determines the position and the sizing. And then we have the paint object. Or for example, a draw circle, which will receive an offset for the center of the circle, and then a double for the radius, which is the sizing. Or draw line, which will receive a position for the beginning point and another position for the ending point. In code, this will look something like this. So here I'm firstly creating a paint object, telling it to be light blue accent with a stroke style and with a thickness of 2 pixels. And then I'm just calling canvas.drawCircle, canvas.drawLine, and canvas.drawRect. And that is how it looks. They all look the same because I'm using the same paint object. Then we have text. We usually use the text widget, right? But if we are painting on a canvas, then it might be better, instead of putting a new widget into our widget tree, just to paint the text there. And for this, we use draw paragraph. This really gives us a lot of control on how we render the text. So for this, we first have to create a paragraph style for like the alignment and the max lines, etc. Then, then we have to create a text style for the font, the weight, the color. Then we create a paragraph builder and we merge the text we want to paint with the styles we just created. Then we call layout to actually give a size to the text box. And finally, we call canvas draw paragraph. I'm going quickly over this. It's not super important, but just so you get the big picture, right? Most of these classes are from the Dart UI package, so it's important you import it before. Then images. For images, we have to preload them and then convert them to image, the class image from the Dart package, the Dart UI package, sorry. And once we've done that, we have to do a lot of logic just to like manually size it and calculate its aspect ratio, just to finally call like canvas.draw image rect in this case. We can see that dash over there. At this point, I think it's important to mention that everything we paint in the paint method works in layers. So in this case, the blue line is over the blue square, and both of them are over the pink circle, right? This in code can be a bit tricky because the first thing we write is what is gonna be in the background. So in this case, we write canvas.drawLine, which is the one that's under everything. Then we write canvas.drawRect, and then canvas.drawCircle, which will be on top of everything. If we want to see this with the example we were previously doing, we won't really notice because we are using the stroke style, right? We know that we are firstly drawing the circle, then the line, then the rect, and on top of them is the paragraph and the image. But if we add filling to these shapes, then we'll see that we are not able to see the circle because it's smaller than the shapes that are on top of it, so they are blocking it, it's hidden. Now let's talk about vertices. They are kind of complex, but super optimized and really used like in the gaming world as well. To work with vertices, we basically have to define positions and then tell them how to connect themselves, forming triangles. So in code, this looks something like this. As you can see, I provide a list of offsets, which are the positions, and it will automatically group them in groups of 3, because triangles have 3 points, right? So it will create this first triangle using the first 3 positions I provided, and the 4th one is going to be ignored. Then we can also provide a list of colors. It must be of the same length as the list of positions, and it will automatically assign each position a color and blend between them. So I didn't have to do like anything specific for that gradient, it's just automatic. And then we can use the indices property to tell it how to connect those positions. So we reference the first list of positions. In this case, I'm telling it to create a triangle using the 0 position, the first position, and the second position, and then a different triangle using the second one, the third one, and the 0. And that's why I got 2 triangles just using the same positions. And last but not least, we have paths with the drawPath method. To draw paths, we have to create a path object, then add a bunch of stuff to it, what we want to actually draw. And lastly, we call canvas.drawPath with that path. In this case, for this smiley face, I added 2 ovals for the eyes and a curve for the smile. We'll talk more about this later. Now let's go through the paint object, which is the one that gives the styles to our drawing, right? So we've already seen that we can manipulate the color and the style, whether if it's stroke or fill. We can also change the blend mode. which will tell the layers how to interact when they overlap. So in the case of the circles, like they are always the same color, but they just change colors depending on the blend mode I chose. Then we can also use a shader, which is a small program that runs in the GPU, so it's super optimized. We can use default ones like image shader or linear gradient, or we can code our own using JLSL, which is the GPU's language. And then we also have image and color filters, which are pretty descriptive. In that case, I used image filter.blur for a blurry filter, and color filter.matrix to create a sepia filter with matrix. We can also apply transformations, so rotate, scale, skew, translate. And we can apply clips. So we define a path that will clip the content that comes below it. And you may notice in these last two slides, we have to use a lot of save and restore, because when we apply transformations and clips, we are applying it to the whole canvas. So if you don't want your whole composition to be rotated, you need to save the current status of the canvas, apply a rotation, transformation, clip, or whatever, and then draw whatever you want to be affected by it, and then restore the previous saved status of the canvas. Now let's go to the actual showcase, the thing I showed you before. So to give you a bit of context, I had the opportunity to work at a project called Trackhouse, which is a NASCAR team. And if you're like me and had no idea what NASCAR was before joining the project, it's basically about the stock car racings. And races happen in stadiums like that one, and it changes every week. And the idea was for people in the pit box, which is the thing in the middle, to have access to a tablet and be able to see like real-time data of the race. And this is how the app came out. It's really cool, but I know there's a lot of information going on here. So as I mentioned before, today we are going to be focusing on the track map feature. But let's do a breakdown here. So in order of layers, what we have to show is the main car, the observed car, which is, I think it's below the main car in the video. That's maybe why you don't see it all the time. And then we have the other cars, which are the gray circles, the start line where the race starts, the track, and the pit stop. To do this feature, we had to take into consideration that races changes from location every weekend. So we have different track maps once a week, right? And these track maps will come from the backend and as SVGs. So what we needed first was to convert the SVGs into Flutter code, right? To be able to use it in our CustomPainter. We probably used SVGs before, right? For icons or logos or illustrations. But let's define what they are. So scalable vector graphics are XML based. They are just that, like vectors, which means that you can zoom up on these images and they will never lose quality. And as they are XML, they are easy to manipulate by code. They also use a coordinate system, just as the one that Canva uses. And then we also have drawing operations, basic shapes, like rect, circle, ellipse, line, polyline, and polygon. Then we have text with the text tag, images with the image tag, and path with the path tag. And you can also apply transformations like translate, scale, rotate, and skew. So yes, they are pretty similar. Probably like the Canvas API from Flutter is based in the SVG, as it's been an industry standard for a lot of years now. I do want to mention that there are some differences apart from the fact that one is XML based and the other one is calls to the Canvas API. Also, like SVG introduces some complexity differentiating between viewbox and viewport. but you can kind of imitate this behavior in Flutter using canvas scale, translate, or fitted box. But apart from that, everything is more or less one-on-one translation. So let's talk about how do we actually translate this. How do we go from SVG to Flutter and be able to use this in our custom painter, right? Let's take this SVG as an example, and no worries, I don't expect you to read this, but let's go step by step and you'll get it. We have a simpler SVG here, which is a circle tag, and we are defining the X and Y position for the center, and then the R is the radius, stroke is gonna be blue, and then the filling is orange. So this is pretty descriptive. We know it's gonna look something like this. But what happens when we have a path tag? When we have the path tag, we have to focus on the D property. The D property stands for definition of the path. So in this D property, we have a string with a bunch of letters and numbers. These are commands. We're gonna go through the commands and how to represent them in Flutter as well, step by step. So firstly, the last line commands. So M is to move the cursor to, so we are not drawing here, just positioning. Z is to close the path, so it's gonna automatically connect the last point we draw with the first one in a straight line. Then we have 3 line commands. L is line 2, so we just trace a line. Then H is a horizontal line 2, and V is vertical line 2, just keeping the axis we want to keep, right? In Flutter, this will translate to path.move2 for the M, path.close for the Z, path.line2 for the L, and the same for the last 2, just keeping the axis we want to keep. We also have the relative commands. As by default, they will take as a reference the 0, 0 position of the whole canvas. But if we use relative commands, then it will take as reference the last dot we drawn. Now let's talk about Bezier curves that are a bit more difficult to understand, but they are super popular. So Bezier curves are basically mathematical curves that are used in vectorial drawing because they are easy to control by control points, right? So it's not only for SVGs and Flutter, like many vectorial softwares also use it. Let's talk about the quadratic Bezier. The command in SVG is a Q, and in Flutter it would be a path.quadratic Bezier 2. Quadratic Beziers, to create one, we need the starting point, the control point, and the ending point. And then it's all about LERPing, which is linear interpolation. So it's like asking Flutter, okay, give me all the points between 2 points. So it's all about that, actually. Like you do a linear interpolation between the starting point and the control point. There are linear interpolation between the control point and the ending point. And then a linear interpolation between all those imaginary points we got in the middle. And that's how you get the curve. But this is done automatically. You don't have to worry about this. So the first 2 parameters will be for the first control point, and the second 2 will be for the ending point. And then we have the cubic Bezier, which is the C command in SVG, and the path.cubic2 in Flutter. And it's literally just the same as the quadratic Bezier, but with 2 control points instead of 1. This one is the most popular one as you have more control over it. So now, if we look again at the path definition, it doesn't look so bad. We can actually kind of read it. We know we have an M, which will be a move to. Then we have 4 Cs, which will be cubics to, cubic Beziers, right? In pink, I highlighted the actual positions. All the other numbers will be the positions for the control points. I do want to mention that there are some differences between vector-based softwares. Like in this case, it's SVG code for the exact same image, one done in Figma and one done in Adobe Illustrator. And as you can see, Adobe will like put all the styles on top and assign classes, while Figma does the styles in line And also Adobe identified that one of the traces I did was a line. So instead of using a path tag, it actually used a line. But there are more differences, like Figma can change the order in which the designer drawn the dots. And that was actually a problem for me because I want the cars to follow the track map in order. So yeah, you may have to take this into consideration when translating. So how do we implement this in Flutter? We want to have the track map converted to a path that we can use in Flutter. So we can do this by using packages. I found the XML package and the path drawing package the best combination. So we will have the SVG as a string. We will do the XML document.parse the SVG. And now that we have the XML document, we can easily find the elements. In our case, we want to find the path element. And after we get the path element, we can get the attribute D, which was the definition of the path. Once we have that string with a bunch of letters and numbers, of course, we check is not null, and we can call parse SVG data with that string. That method is from the path drawing package that I just mentioned, and this will just return the path object. We can also do this manually. We don't need packages. This was the first approach in the project. I wanted to show it to you so you see like it's not so difficult. In this case, I had a function method with a regex just to get this definition of the path, the string with a lot of letters and numbers. And after I have that string, it's just a matter of iterating over it and asking like, is the letter an M? Okay, then do a move to. Is the letter an L? Then do a line to. And if the letter is a C, then do a cubic to, assigning the corresponding numbers to each method, right? And if you're curious, you can also check that in the path drawing package, they are doing something like that. In their GitHub, in the parse path file, you can see that they end up using the same commands, cubic to, line to, and move to. You may ask, can we use Flutter SVG in this case? Because it's the most popular package when working with SVGs in Flutter, right? But the thing is that no, we can't, as it's not a SVG toolkit. Its job is just to render the SVG as fast as possible. So in the background, it's just the binary commands that we can control. So in this case, it wasn't useful. So to recap, now we do have this track map as a path. We can use it actually in our CustomPainter. So how does the CustomPainter looks for this feature? It looks something like this. Don't worry, I don't expect you to read it. It's just to see the structure. And on top of everything, I'm setting the painters, because you will need a painter for the other cars, then the border of the main car, then the filling of the main car, and etc., etc. And then I'm just overriding the two mandatory methods I mentioned before. Let's check the paint method, which is where we are actually painting. And as we know, this is the order of the layers. Then we will know that if the main car has to be on top of everything, it's going to be the last thing we draw. And if the pit stop is in the background, it's going to be the first thing. So we can see that we do canvas.drawPath for the pit stop, then the track. Then we paint the start line. And then we do iterate over the other cars to paint all the gray dots. And then we call paint pilot for the observer card and the main car. We keep that order. We won't have time today to go through all of the methods, but I wanted to show you the paint pilot or paint car method, because I feel like it's the one that showcases the best all the tools we have available. So this is the method. And the first thing we do is, as you can see, oh wait, I mentioned one thing. As a parameter, we will get the percentage which will represent the position of the car. So the whole loop of the track will be 100%. And we can get like 28%. What does that mean? Where should we put the car? Like, what is 28% in the truck? So to figure that out, we first do path, so the path of the truck, dot compute metrics. Compute metrics will provide us with a list of the path metrics we have for a path. So a path metric is basically a contour, which is a drawing, a non-stopping drawing, let's say. So in this example path, we will have one contour, then we do a move to, and we have two contours, and then we do a move to, and we have three contours. So if we do a compute metrics from this path, we will get a list of 3 path metrics. And from the path metric, we can get the length, the tangent vector, which will also provide us with the direction. And we can extract path and know whether if it's close or not, and more stuff. So you may wonder what's the length of the path. So to calculate it, like Bezier curves, they are only flow that you can't actually know the exact length of it, but you can get a very approximate by doing short lines, straight lines, getting the length of them, and then adding them together to know the approximation. If you are interested in this and the math behind all of this, I recommend you to check the video, The Beauty of Bezier Curves, on YouTube. So once we have all the contours for this track, we can actually know the length of each one of them, and sum them up together, and then we get the total length of the track. Once we have that, as you can see in the target distance, we should use the percentage, for example, 28%, times the length of the track. And that's how we know which should be the position of the distance the car has driven through the track, right? Once we have that, it's a matter of iterating over the different contours to see which one contains this distance. And when we find it, we can do get tangent for offset, which will give us the position, which is the exact pixel in which we have to draw the car. So once we have the pilot position, we can simply do canvas.drawCircle for the outer border, canvas.drawCircle for the inner border, and then canvas.drawCircle for the filling. Then just put the image, and we have the car using always the position we calculated before. And this is the result, basically. Before leaving, I wanted to give a huge shout out to the whole Trackhouse team, because of course I didn't did the whole app by myself. Kyle Kraus, that he was around here somewhere, he is the mastermind behind the whole project, so if you have more doubts, he probably be at the BGB booth. And then Dan, the designer, and Shannon Ayal, who were the developers with me. And that was it for today. I'm also leaving a QR code for you in case you want to check the slides. And I'll be around if you have questions. I don't know if we have time left for questions. But yeah, that was it.